share that. And you got my slides?
Yep.
Fantastic.
Yep, just take it away.
All right, thanks. I'm sorry for the glitches, but hopefully we'll be able to get through this without any more of them. So getting right into it, I'm going to try to talk a little bit about the sort of really hot topic right now, the string Swampland. And to start with, I want to point out that I'm going to take a pretty kind of a slightly different perspective on it than you might hear from a lot of people, in the sense that this is very clearly, these ideas are very clearly extremely useful for formal theory development and understanding and figuring out how you're going to categorize different, different approaches to effective field theory in a quantum gravity context, and so on and so forth. I'm not an expert in that, and I'm not going to talk about it. What I'm going to talk about more is looking at the swampland from a phenomenological perspective. And what I mean by that is we have lots and lots of data about dark energy, about inflation, and so on and so forth. And what I want to talk about is how we actually sort of, how the data and the ideas of the swampland actually meet, and how well they fit together. So this is going to be a very strongly phenomenological talk. And talking to you guys, I decided to give a sort of a colloquium level talk, fairly pedagogical. So I apologize to the specialists in the audience for whom the first half of this talk is going to be a little dull. So that what I'm going to do for the first part of the talk is just give a very a pedagogical overview of inflation itself, and this is going to be really where I'm going to be focusing, is looking at the swampland and inflation. And then in the second half, I'm going to talk about, give an introduction to the swampland ideas with a focus on how it affects inflationary model building and phenomenology. Okay, so let's go from there. So here's the data that is most important for constraining inflation models. We're all familiar with this picture. This is the Planck sky map of the primordial perturbations. And this is, as you know, a tremendously rich data set that allows us to put really strong constraints on early universe physics. And something that I like to show in these talks is just how far we've come in, say, the last 20 years or so. So this was the state of the art in 1998. This was a figure that Max Tegmark put together, summarizing all of the known, all the existing data on the cosmic microwave background multipole spectrum, right? So you take this spherical sky, you bust it up into spherical harmonics, and then you plot the amplitude of the spherical harmonics by their multipole number. And this was where we were as of about 1998. You were just barely, basically starting to see the first outlines of that first acoustic peak happening here. So you had Saskatoon was showing the rise right around a multipole of 200. And then you have observations like Ring and Cat that were actually showing the fall off after that. We've come a long way. This is the Planck 2015 data for that same angular power spectrum. And the black line is a best fit lambda CDM model. The red dots are the data from the bin data from the Planck satellite, when the blue lines are the error bars here. It's interesting to note that, of course, that this is cosmic variance limited out to a multipole of about 2,500 or so, which means that this is an essentially theoretically perfect measurement of this temperature autocorrelation function in the CMB. We're never going to do any better than this with this particular bit of data. Planck has essentially nailed it down perfectly. And lambda CDM is an excellent fit. So here's a plot of the residuals relative to Planck. And what we see here is that the lambda CDM model is now this flat line. The best fit lambda CDM model is this flat line. And for all intents and purposes, it's a statistically perfect fit. With the caveat, of course, that this is a fit to an H0, a Hubble parameter of 68, which is in pretty strong conflict now with data from things like type 1a supernovae and quasar lensing time delays. So there's that mystery. I'm not going to talk about that here because it's not terribly relevant for inflation model constraints per se, or at least the kind of constraints I'm talking about are going to have very little to say about that particular problem. You know, maybe it will turn out to be a systematic, maybe it'll turn out to be new physics. I don't know. I'm just going to leave that sitting there for the purpose of this talk. So this data is this basic lambda CDM 6-parameter, 7-parameter model is well explained by the physics of inflation. So the leading theory of the early universe that we have to explain this is inflation, which broadly speaking, when I say inflation, what I mean is some period of accelerated cosmological expansion extremely early in the universe. What that's driven by, what kind of physics is creating it, we'll be agnostic to that. As long as basically any physics that is going to cause this accelerated expansion, as long as we can visualize it as a phase transition involving one or more order parameters that are given by a scalar field. So it could be supersymmetry, it could be fundamentally string driven, it could be caused by any number of collective phenomena, but we're always going to take those collective phenomena and reparameterize them as essentially something that's got in most cases that we'll be talking about today, a single order parameter, which is a single scalar field. The identity of that field is entirely unknown. But as long as we just make that assumption, as long as we assume that we've got a phase transition that's governed by a single order parameter, we have a number of unambiguous predictions that come out of this. In particular, that we have adiabatic density perturbations, which is well consistent with the data. There's no evidence for example, isocurvature modes and the like. Gaussian statistics, the Planck limits on non-Gaussianity are now extremely strict with an FNL of order a few. And that is well predicted by a simple scalar field, canonical scalar field model predicts you should have anisotropies of the order of 10 to the minus 2 or so. And perhaps most important of these three is superhorizon correlations. The idea that the anisotropies, the primordial density perturbations in the universe, are actually correlated on scales larger than the horizon size, for example, at the time of the cosmic microwave background is emitted. And it's these superhorizon correlations that really form the, if you like, kind of the smoking gun for inflation, at least in the absence of any sort of tensor perturbations. So to visualize this, let's visualize the flat expanding cosmology as sort of a grid of squares extending infinitely off in all directions, right? So this satisfies the cosmological principle. Every point is the same as every other point. There's no center and no edge. It's homogeneous and isotropic. As long as this grid is either infinite in spatial extent or on a non-trivial topological manifold. And the expansion of the universe then is just all of these squares that we draw on this grid growing bigger and bigger and bigger with time. And likewise, going backward in time, we find that if we turn the clock around backward, all these squares shrink and eventually go to zero size at finite time in the past, which is the Big Bang. Note that the space, even infinitesimally after the Big Bang, is infinite in spatial extent. So the standard hot Big Bang model doesn't explain this homogeneity because, in fact, the horizon of the universe is going to be very tiny, even though the space is infinite in extent. And mathematically, we can describe this by standard Robertson-Walker metric. So we just take, for example, by analogy to special relativity, we have a proper length that's given by dt squared minus dx squared. In order to modify this metric to represent an expanding space, we simply multiply it by a time-dependent scale factor, which we'll call A of t, which is also useful to factor that out so that we have an overall dimensionless conformal factor times an effectively Minkowski metric. In this representation, this is essentially conformal time, means measuring time with a clock that slows down with the expansion of the universe. We find that light cones, just like in special relativity, are just 45-degree angles in our space-time. And the expansion isn't just a conformal factor that sits out in front of that. So when we look at it in this way, for example, we can look at the difference between a cosmological Robertson-Walker space and a Minkowski space. By looking at, for example, in a Minkowski space, if we have an event here, our future light, the causal future of that event is all of the points inside its future light cone. The causal past of an event is all of the points inside its past light cone. But in a Robertson-Walker space, where the universe has a singularity at finite past time, it looks exactly causally like a Minkowski space, except that the past light cone is cut off at some finite surface, some infinite surface in the past, which is the Big Bang singularity. So that when we're here looking back along our light cone, no matter what direction we look in the sky, what we see is we can only see out a finite distance. That distance is our horizon, or the amount of time that light has had a chance to travel, the distance that light has had a chance to travel in the finite time since the Big Bang. So in that sense, our horizon distance is just the projection of our past light cone on this surface of initial singularity. You can also plot it on this other plot where for example, in a standard matter-dominated expansion, for example, you might have two observers who are separated by larger than a horizon distance. But as the universe expands, and this is like essentially a relative effect, a local effect, much like the horizon on the surface of the Earth. Everybody sees a different horizon about them. If you're standing on the Earth, you see the horizon at a different place. Likewise, people in a Robertson-Walker space are going to see, each is going to see their own horizons, which may or may not overlap. As the universe expands with time, that horizon grows, and eventually two observers that are outside each other's mutual horizons fall back into each other's horizons again, and they become causally connected. Now, inflation modifies this picture in the following way. We add negative pressure, and in particular, so that if we have a pressure less than minus 1/3 the energy density, that means that the rate of change of the scale factor is increasing. The expansion of the universe is speeding up. We know that this can happen because it's happening in the universe right now. Dark energy is causing accelerated cosmological expansion. Likewise, in inflation, we postulate that happened in the very, very early universe, and that this acceleration was extremely rapid. And the extreme case of this is a de Sitter space, where you have a cosmological constant, where the expansion rate, the Hubble parameter, is a constant, which tells you that the expansion is exponentially quick. And the time factor in the exponential is just the inverse Hubble time, is given by the Hubble time. And in particular, this means that the space-time actually expands faster than the cosmological horizon. So unlike in the example I showed you just a minute ago, if I have two observers that are inside each other's mutual horizon, they're receding from each other at less than the speed of light, as the expansion, as the inflation takes place, since the Hubble parameter is approximately constant, that means the horizon size is approximately constant. The Hubble distance doesn't change, or only changes very slowly during inflation. But the space itself is expanding exponentially quickly. So this observer is exponentially rapidly shifted outside the horizon of the second observer is exponentially quickly shifted outside the horizon of the first. This is the key property that allows us to generate perturbation modes that are correlated on superhorizon scales. The basic idea here is that you start out at early times with a mode that is with a quantum mode inside the horizon, but the exponential expansion exponentially quickly stretches that mode to outside the horizon, and it is stretched outside the horizon. The quantum mode becomes classical. You have mode freezing, and you generate superhorizon correlated cosmological perturbations. So this can be done in a cartoon diagram like this as well, where what I'm plotting here is the log of the scale factor on the horizontal axis. So, and on the vertical axis is just the log of the physical wavelength of a wave mode that is expanding, redshifting along with the cosmological expansion. So this blue line is just a wave mode that is expanding, that is stretching proportional to the scale factor, which is what you expect from the Friedmann equations. And the red line here is the behavior of the Hubble parameter, the Hubble distance, H inverse with time. During inflation, it's almost constant, slowly decreasing as long as you have as long as you're not quite in de Sitter space, which we know we're not, because of the fact that the primordial power spectrum is a little red tilted. And then after the inflation ends, you enter a period, say, of radiation domination after reheating, and the Hubble parameter begins to, the Hubble length begins to increase. The horizon size of the universe starts to grow, and this mode, which was during inflation stretched outside to a wavelength longer than the horizon size, at some later point then falls back into the horizon as a classical perturbation and source of structure formation. Another way to see this is to just plot the amplitude of a quantum mode, right? So this is actually solving the Klein-Gordon equation for a quantum mode in a de Sitter background. And what you find is that on the horizontal axis is the wavelength in units of the Hubble length, and on the vertical axis is just the amplitude of this curvature perturbation mode. what you find is that this is oscillating as a quantum mode when it's shorter wavelength than the horizon, but gradually as it stretches out, as it stretches to superhorizon scales, the oscillation ceases, the mode becomes non-dynamical, and the mode freezes out with a finite amplitude. And that amplitude is calculable and needs to be on the order of about 10 to the minus 5 for it to match cosmic microwave background measurements. So this is the mechanism in inflation, the stretching of quantum modes by the exponential expansion that is responsible for setting the boundary conditions for the cosmic microwave background. So the neat thing here is that we can take particular inflation models, calculate the evolution of this quantum mode in the Klein-Gordon equation. It's all a very well-defined calculation. And so for a given choice of inflationary potential, for example, we can calculate the shape of the power spectrum that's generated in the primordial perturbations, compare that to the cosmic microwave background. So this is the name of the game in cosmological phenomenology or in inflationary phenomenology, is we do this calculation for these quantum modes in an accelerating background. We can actually calculate what the expected form of the cosmic microwave background should be, and then we can compare that phenomenologically to data. So once again, in inflation, we have some sort of potential surface. When inflation happens when the cosmology is vacuum dominated. So when the ball is sitting up on top of the hill here, the ball rolls off the hill. Expansion introduces dynamical friction, which gives us a state of slow roll. The ball gradually rolls off the hill, eventually reaches its vacuum, oscillates about this, creates particles, and reheats the universe. So, but the shape of this hill is what determines the outcome of what determines the form of the perturbation. So if I look at different choices for how this hilltop or how this potential surface in general is shaped, then I make different predictions for the generation of modes. And I generate, in inflation, you generate generically two different kinds of primordial perturbation modes. One is gravitational waves. So because of the fact that gravitational waves act like a scalar field in this background, it's a generic prediction of inflation that you should be generating these superhorizon tensor modes, these gravitational wave modes in the background. The amplitude of those is not a generic prediction, but the fact that they should be present, it should always be true no matter what inflation model you look at. The second kind of perturbation you generate in these sort of models is density perturbations, because the inflaton field, this order parameter that's evolving during inflation, is coupled to the energy density during inflation. That means that quantum fluctuations up or down this hill are going to then get realized as perturbations in the density of the background universe, and thus it will give you perturbations in the scalar perturbations or perturbations in the density, which is mostly what you're seeing in the cosmic microwave background. And so you can plot this. So there are two basic observables here, the tensors and the scalar modes. And you can plot this as follows. Both of them are predicted to be power laws. And so this is probably a familiar plot to most of you. On the vertical axis is the tensor-scalar ratio. That is, what fraction of the cosmic microwave background perturbations that we see are due to gravitational wave modes. So a tensor-scalar ratio of 0.2 means that the CMB anisotropy is 20% due to gravitational wave modes and 80% due to density perturbations. R of 0.1 means that 10% is gravitational wave modes, and so on and so forth. On the horizontal axis is the tilt of the scalar perturbation spectrum. So this is the density perturbations now, and these are predicted to be a power law in any simple inflationary model. And in fact, to a very good approximation in the data is very consistent with a power law form for these density perturbations. And the tilt of that power law is given by a scalar spectral index. And n is equal to 1 means completely scale invariant perturbations, that the amplitude of the primordial density perturbations is the same at every length scale. The deviations from that scale invariant n sub s is equal to 1 limit, which is the case, for example, if you have a pure de Sitter background, are given by the first and second derivatives of the potential itself. So this scalar field potential that's responsible for inflation, I can calculate its first derivative and its second derivative during inflation, and the values of those derivatives actually determine the tilt of that primordial power law for the curvature power spectrum. And what we know from Planck is that that's slightly red tilted. It's not quite scale invariant. It actually has slightly more power on large scale and slightly less power on small scales, with a best fit of about 0.96 or 0.97 for the scalar spectral index. The tensor scalar ratio is also determined by the shape of the potential, but only by the first derivative, not by the first derivative and the second derivative. So the name of the game here is that we can take the Planck data, for example, place constraints on the tensor scalar ratio. For right now, all we have is an upper bound of about 0.05 or 0.07 or so. And a bound on the scalar tilt, which is about 0.96 or so. So on this plot, these red regions are the 1 sigma and 2 sigma confidence allowed regions by Planck. So the Planck data tells us we live somewhere within these red patches here. And then if I choose different choices for the inflationary potential, for example, an m squared phi squared here, an exponential here, a linear potential here, or here's the Starobinsky, the 1 minus an exponential, these put us in different places on this plot of tensor scalar ratio versus spectral index. So we can actually distinguish the predictions of one model from another in this particular observable space of models. And here's what the data look like relative to actual, several just representative choices for the scalar field potential. These sort of m squared phi squared or even linear potentials or exponentials, these things that are basically these what are called chaotic inflation models, are now pretty strongly ruled out at quite a few sigma, whereas these plateau or hilltop kind of a models like this representative of the Starobinsky case, which is a plateau model, are a good fit to the data. So we've done, the Planck data are really remarkable in that we can actually take particular models for this very early phase of evolution of the universe and actually rule them out, distinguish one from another, and some of them will be consistent with the data and others will not. Here's a similar plot except with more models on it and the y-axis logarithmic instead of linear. And so what we see here, for example, is this is the axion monodromy model, which is motivated by string theory. Here's this natural inflation model where the inflaton is something akin to a QCD axion. Here's a Coleman-Weinberg potential in these green lines, for example, various other leading order operators for the hilltop, these sort of very flat hilltop models like this that are a good fit to the data. Here's this Starobinsky potential, which is basically turning an R-squared gravity model into an Einstein frame theory that results in this one parameter scalar field potential that hits the data absolutely right on. So this is really a huge success, right? We have had this whole process of figuring out how to calculate what different inflation models predict, and now the data are finally at a point where we can compare that, and we've got like remarkable data. And the situation is going to continue to improve. So this dotted line here is the target sensitivity for example, CMBS4. So this is a couple generations ahead in what we expect to be able to do with, in particular, measuring cosmological B modes in the cosmic microwave background. So these future cosmic microwave background measurements are aiming to get down to a couple times 10 to the minus 3, which would be capable of actually ruling out, in principle, if we got an upper bound, if they didn't see anything, it would then rule out these Starobinsky type models as well, or we could show that it was consistent. So the future is bright. There's a lot that is going to be a lot of development that's going to continue on the observational front. And if we're lucky, we may actually start to see evidence for these primordial gravity waves, which would open up an entirely new channel for observing the universe. It would be just a cornucopia of good things that we could measure and start to really understand what's going on in the early universe. So an example of one question that we can ask and answer with current data is, what kind of potential fits the data best? One of these convex potentials, like an m squared phi squared, where it's this is the kind of the basic model for Linde's chaotic inflation, Or does it look more like this, where inflation is like a Higgs boson or something like that, a spontaneous symmetry breaking potential where the field is rolling off the top of a hill? We can answer that question with current data. So here is the RN plot now, and what I'm highlighting here, so this is once again the plot 68 and 95% confidence allowed regions. And here is the dividing line between essentially a V double prime, a positive second derivative for the scalar field potential, and a negative second derivative for the scalar field potential. And what you find is that, to better than 95% confidence, we know that the second derivative of the potential during inflation was negative. And here's this linear model which lies on the boundary between the two. So this is really neat because we can just state this in a very simple and general way, is that this kind of a potential, these upward tilted bowls, they don't work very well. They don't match the data. But this sort of thing that's like something akin to a Higgs boson works really, really well. It's an excellent fit. So we know a little bit about what's going on in inflation. Not a whole lot. I mean, we're hardly reconstructing the form of the potential, but at least we have a qualitative picture of what kind of physics we're looking at when we're talking about inflation in the early universe. So now let's move on, right? The new question that has been coming up in string theory, right? So presumably this potential is going to have something to do with quantum gravity. The energy scales involved are up around, probably around 10 to the 14, 10 to the 15 GeV. So the natural place where you're going to start model building for this is effective field theories that are based on quantum gravity. So some sort of gut scale physics that is going to that you want to integrate into some larger UV complete theory. So you're really interested in the question of how do we reconcile this sort of inflationary picture of this spontaneous symmetry breaking, this field rolling off the top of a hill at very high energy and driving accelerated expansion for at least 60 e-folds. Not only does the cosmological expansion have to accelerate, but it has to go on for long enough to generate all of those wave modes that we see in the universe today. So the big question now is, okay, so is inflation part of the swampland or part of the landscape? Is it consistent with what we know about UV complete theories, and is it something that can be consistently embedded in a UV complete theory? And the paper that we wrote on this a couple of years ago now is with myself and Sonny Vagnazzi and Luca Vicinelli, who were at the University of Stockholm at the time. And so we looked at this question of what do these swampland conjectures tell us about inflationary model building? What do they tell us in particular about this phenomenology on the RN plane? So what do I mean by the swampland? Well, in order to understand the swampland, you have to understand the landscape. So the basic idea of the string landscape is that you have to compactify a 10 or 11 dimensional space down into a 4-dimensional one. And there are a lot of different ways to do that, to wrap up those extra dimensions and make them small enough so that we have an effectively 4-dimensional universe. So the estimate is that there are about 10 to the 500 different ways to take this larger space and compact it on a calabi-yau down into a smaller space. And all of those different ways of doing it can be parameterized by a set of scalar fields, by a set of moduli fields, right? So as these dimensions stretch or shrink, that then can be mapped to the evolution of scalar fields in this moduli space. And so you end up with this sort of very high dimensional, very complex potential surface called the landscape, where all of these different ways of compactifying your manifold represent different vacua, different minima in the space of these associated moduli fields. So I have a whole bunch of scalar fields. I have an incredibly complex multidimensional potential surface for those fields. And as the universe compactifies, it rolls down, finds itself in one of these minima. What minimum you're in is what determines what low energy effective field theory you're seeing in the vacuum. So what kind of symmetry, for example, this one might be SU2 cross SU3 cross U1. This one might be some other, an SO10 or something like that, right? So the symmetries that you see in the standard model are just in this picture essentially an accident, a result of which one of these many, many 10 to the 500 vacua you end up with. So this manifold, this complicated set of moduli fields with the 10 to the 500 different vacua is referred to the landscape, the set of all possible low energy field theories that you can get out of compactifying your string theory, your higher dimensional string theory. So to repeat that, the landscape is the set of all possible low energy effective field theories that are consistent with your UV complete theory, for example, string theory. Now, the other question is, you can look at this the other way around. So suppose I have a low energy effective theory. I can just write down some Lagrangian. I can ask the question, is that part of the landscape? Does that low energy effective field theory actually have a representation as a compactified state of a string theory? And this is viewed, okay, there we go. So the metaphor for this is now the swampland. So imagine a swamp with like some areas of land, some areas of swampy water, and so on. And in this picture, the islands, the land in the landscape is going to be, all right, come on. The slides are changing very slowly. You guys still there? Say hi if you're
Yeah,
still.
we're here.
Okay, good.
You're lost in the swampland.
I'm lost in the swampland, yeah. Oh, there we go. It's back. All right. So now we can say, okay, all these different possible string vacua that we might have are sort of like the dry spots. These are the places where you can sit and you can make a coherent theory. But on the other hand, in between them all is all the swampy parts, the places where, in fact, you can write down an effective field theory, but it doesn't correspond to anything that has any kind of a UV complete theory associated with it. That's the swampland, is these regions in between these effective field theories that don't have any representation in a UV complete theory. To give an example of how this works, let's talk about the weak gravity conjecture, which is probably the oldest one of these swampland conjectures and arguably the physically best motivated. So to understand this, basically look at a charged black hole, a Reisner-Nordstrom black hole, which, as we know, has two horizons, one associated with the charge on the inside and one associated with the mass on the outside. Now this thing is going to Hawking radiate, right? So imagine if Hawking radiates a charged particle, that charge horizon is going to shrink, and gradually that will get smaller and smaller, and you'll get closer and closer and closer to essentially like a Schwarzschild black hole, right? So this is fine. I can radiate away charged particles, and this inner horizon gets smaller as I radiate away charge. Now, suppose I do the opposite. Suppose I radiate away massive particles that don't carry away the charge. The opposite happens is my outer mass Schwarzschild horizon shrinks, but the inner horizon associated with the charge of the black hole doesn't. And so eventually what happens is, as I radiate away mass, if I don't radiate away an equivalent amount of charge, eventually I get to an extremal state where the thing can no longer Hawking radiate, because you cannot have a Reisner-Nordstrom black hole where the charge horizon is bigger than the mass horizon. And this is bad. It violates all kinds of entropy bounds. You end up with stable relics that tend to overpopulate the universe. So the concept here of the weak gravity conjecture is that you must at all costs avoid this condition where you have a black hole that Hawking radiates down to an extremal Reisner-Nordstrom state, where the charge and the mass horizons are the same size. So I can always do that as long as I radiate away charge faster than mass, right? And so that gives me a condition on the particle content of my effective field theory. That tells me if I must always be able to radiate away charge faster than mass, that tells me that my low energy effective theory must always have at least one light charge state, something where the mass is smaller than the charge. There must be at least one particle in my effective field theory with mass smaller than the charge to enable me to radiate away that charge so that I don't end up with stable Reisner-Nordstrom black holes. So I have this global condition, for example, on the absence of extremal Reisner-Nordstrom black holes that I can then translate into a condition on the particle content of my effective field theory. This is how swampland conjectures work. So let's talk about ones relevant for inflation. The first one is there are basically two swampland conjectures associated with de Sitter space. The first one is the distance conjecture. That tells me that if I have, for example, some compact string manifold, so this is some Calabi-Yau where I've compactified by string theory, the typical scale at which this happens is going to be somewhere around the Planck scale. This is a quantum gravity theory. So I expect that my scalar field excursion can't be much bigger than the Planck mass, because there's just not enough room inside that Calabi-Yau for it to happen. So the first conjecture here is that any UV complete effective theory must have, if I'm looking at one of these moduli field, that moduli field can't have an excursion much bigger than the Planck mass. Otherwise, it doesn't make any sense as a low energy limit of a string theory. The second Swampland conjecture, remember, I have an inflationary potential. Here's a cartoon of a typical slow roll potential where I have this big flat plateau up here where the scalar field is slowly rolling along a very narrow slope, and this is characterized by some height and some width. And so the distance conjecture tells me that the field excursion, or this characteristic width of this potential, has to be less than or equal to around the Planck mass. But there's a second conjecture as well, which is the de Sitter-Swampland conjecture, which tells me that the change in potential over the potential itself in units of the Planck mass has to be something of order unity. That is, the potential can't be too flat, that it has to have a minimum steepness. The first derivative of this potential has a minimum value in order for it to be a standard UV complete theory. Okay, that's the conjecture. What is that? So I'm not going to comment on how that conjecture works into, how one constructs the string theory or whatnot. I want to ask the question, how well does that stay consistent with data? If I want to say I'm going to construct an inflation model that is going to obey these two conjectures, first, that the field excursion has to be small, and second, that the potential has to have a minimum steepness, how well can I do? How well does that match with what we see in the cosmic microwave background? And the answer to that is pretty terribly. So here is, in this constant should be, according to the de Sitter-Swampland conjecture, a constant of order unity. What you find is that the upper bound you get from the tensor scalar ratio, from the absence of gravity waves in the cosmic microwave background, is that can't be larger than about 0.1. And then if you're talking about bounds that are consistent with, say, CMBS4, where you're going down to 10 to the minus 3 or so, this constant ends up being incredibly tiny. So the best fit models of inflation right now are in some pretty good tension with the de Sitter-Swampland conjecture. And if these bounds get smaller and smaller, if we put a bound of 10 to the minus 3 or so from CMBS4, they're going to be in very strong tension. That means that either you abandon inflation, or you have to abandon these one or more of these conjectures for understanding the UV completion of a low energy effective theory. What this is telling you is that a low energy effective theory that is consistent with inflation is already in quite strong tension with these conjectures about UV completion for moduli fields in string theory. Now, this isn't the end of the story, because not long after the de Sitter-Swampland conjecture was proposed, it was realized that they had to fix it a little bit, because, for example, it wouldn't allow the Higgs boson to exist, because a spontaneous symmetry breaking potential is always going to have somewhere on its scalar field potential where that first derivative vanishes. So in fact, a standard symmetry breaking potential for the Higgs would also be inconsistent with the de Sitter-Swampland conjecture, formally speaking. So that this was fixed up by proposing, so that in fact that you will always have a spot on this potential where V prime over V is 0. And so Oguri et al. Published a paper subsequently in December of 2018, suggesting that you had to modify this slightly in order to account for this possibility, where either you had a potential that was sufficiently steep, or it had a sufficiently large curvature, that V double prime over V was sufficiently negative. And in that case, that would allow this case, because V double prime over V has to be big enough so that you just have to have a hilltop that's curved enough, and then you have spontaneous symmetry breaking. There were other technical reasons for proposing this as well, but this is the simplest sort of counterexample that you can think of. So that in the case where this V double prime over V is small, you have to have this large negative V double prime, and then you're okay. This is called the refined Swampland conjecture. And we can actually now say, okay, so if we allow this refinement, if we allow this sort of exception to the de Sitter-Swampland conjecture, what does that do for us, right? And and here's what we find is that if we plot contours of this refined Swampland conjecture, we find that we're still in tension with it. Even if we allow ourselves to have a small enough slope, The curvature of this is limited by, in particular, remember that the scalar spectral index is determined by both the first and the second derivative of the potential. So we can put bounds on the second derivative as well from data. And what that tells you is that this is still in strong tension with even the refined swampland de Sitter conjecture, in that the curvature of this potential is constrained to only be of the order of 10⁻² in order to be consistent with data. So takeaway here is that if you buy the de Sitter swampland conjectures, then what you are also going to have to get with it is a very strong tension between that and any possible single field inflation model. There are ways to work around it, for example, worm inflation or multi-field inflation and so on, but the tension is real and it's very strong. It tends to, if you accept the swampland conjectures, you tend to reject inflation altogether as a consistent UV complete theory of the early universe. So this is the consequences for inflation here are profound. It really, these kind of conjectures really create a strong tension with the inflationary phenomenology. So in the last couple of minutes here, let me talk about Transplanckian censorship. I know I started late, so I want to try to finish up as close to on time as I can, but I want to talk a little bit about this because this is some interesting work I've been doing with my graduate student, Wei-Chen Lin. Is that there's, last year there was, Bedroya and Vafa proposed another conjecture, and which is related to the de Sitter swampland conjecture, at least in canonical theories. That the idea here is that, remember, we take short wavelength modes and stretch them to long wavelengths in inflation. So here's this diagram of mode stretching and freezing and inflation again. Well, there's a problem with this, which is that the initial wavelength of this mode, when you set the boundary condition, the Bunch-Davies vacuum and so on and so forth, is mighty, mighty close to the Planck scale. So in particular, the Transplanckian censorship conjecture says that you cannot take a mode whose initial wavelength is shorter than n Planck inverse and stretch it out to super horizon scales. So this is forbidden. Now, a long time ago, me and a whole bunch of other people wrote a whole lot of papers about the possibility that you could have these Transplanckian modes stretched to astrophysical wavelengths and actually use them as tests of string theory. This has now been turned on its head, and the current thinking is that this has to be impossible, that this is just a fundamentally inconsistent process. So basically speaking, if I have a way, this particular evolution would actually violate the Transplanckian censorship conjecture, because I would be taking a Planck wavelength mode, stretching it out to super horizon scale. So I would be taking something that had a quantum gravitational boundary condition and turning it into a classical mode. Transplanckian censorship is that that's impossible, that such a thing is not allowed, which means that any modes shorter wavelength than that can't be stretched out larger than the horizon during inflation. And the consequence of this is obvious from the diagram, is that means that the duration of my inflationary expansion has an upper bound, that I just can't inflate for too long. Otherwise, I'm going to run afoul of this Transplanckian censorship, because I'm going to be, if I'm stretching modes for enough time, eventually I'm going to start stretching Planck length modes out to astrophysical wavelengths. And the Transplanckian censorship says that's bad. This is the basic picture in a canonical theory. Now, the work that we did was looking at non-canonical theories, which are well known in string theory, right? So if you want to talk about things that actually have realizations in UV complete theories, you really want to be looking at non-canonical theories as well. For example, and a good example of this is DBI inflation, in which you have a brain evolving in a throat, either going down the throat or up the throat. And in that case, what you have is, in fact, you have a non-canonical field theory. And what this means is you have a speed of sound that's less than the speed of light. You actually have a dynamical speed of sound. In a canonical theory, the speed of sound is always equal to 1. In these non-canonical theories, you have a time-varying sound speed as well. And a nice way to represent this is I can rewrite this as something that looks like a canonical scalar field theory, but it's a bimetric theory now, where I actually have a different metric, big G mu nu, that is governed, that instead of determining the light cone, determines the acoustic cone, the propagation length for sound waves in the inflationary fluid. And this acoustic cone during a DBI inflation is going to be smaller than the Hubble length, because the speed of sound is smaller than the speed of light. This means, and it turns out that when you do the calculation, you write down the Klein-Gordon equation for perturbations in this case, modes freeze out not at the Hubble length, but they actually freeze out and become classical at the acoustic length. That means in these DBI theories, remember ones that we know we can construct in string theory, that this Transplanckian censorship is going to be stronger than it is in a purely canonical theory, because the freeze out length is actually going to be shorter than the cosmological horizon. So in particular, here's a diagram of the TCC in a canonical theory. So what we suggest is that you actually, in the case of non-canonical theories, like these ones we know in string theory, you have to generalize this to, and so now let's zoom in on this picture. So here's this mode wave, well, I'm pointing at the screen with my finger. Here's this wave mode that saturates the Transplanckian censorship, right? So you know that any modes to the right of this thing are forbidden. But now imagine that I have some sort of dynamically evolving sound speed, in particular that this green line shows if I have a speed of sound that's decreasing with time. For example, if I'm rolling down toward the tip of the Klebanov-Strassler throat, what I'll find is that this will behave like a power law. And in fact, my freeze out length is now no longer going to be this red line, the Hubble length, but modes are going to freeze out when they cross this green line, which is the sound horizon. So this is the point at which the quantum to classical transition takes place. And in particular then, if I have so there are two effects here. One is inflation has to start earlier. For a given time evolution of the Hubble length, you have to go back further because the sound horizon is smaller than the Hubble length. So instead of the earliest mode exiting, instead of inflation starting here, I have to go a little bit back in time. And secondly, Transplanckian modes are going to exit this acoustic horizon a lot earlier than they would exit the Hubble length. And in particular then, in order to say if I'm going to have no Planck scale modes that become classical, I have to start here and actually go and rule out modes that cross the horizon outside of there. So it fundamentally changes the kind of bounds you get on your inflationary models when you consider these generalized theories of the type that you really actually expect to see in string theory. And so this is this paper that I wrote with my graduate student, Wei-Chen Lin, looks at the bounds on this. And in particular, one of the big takeaways here is the Transplanckian censorship in a canonical theory. There's a direct relationship between censorship of Transplanckian modes and the de Sitter-Swampland conjecture. That Oguri et al. Actually derived the de Sitter-Swampland conjecture from the TCC. And here you can no longer do that because the acoustic horizon is dynamically independent of the Hubble length, and so it breaks that link between Transplanckian censorship and de Sitter-Swampland conjectures. And in particular, in these models, you can have inflation happen on a very steep potential, for example, so that you no longer have that relationship between Transplanckian censorship and de Sitter-Swampland conjectures. So that's an important takeaway here, is that relationship between those two is only valid in a canonical theory and not in a general string theory. So to wrap up here, let's just ask the question from a phenomenological standpoint is, should we be taking these conjectures seriously, right? They're certainly useful for string theory. I mean, if you look at it from a point of view of formal theory development, they're tremendously powerful tools. But for me as a phenomenologist, as an inflationary model builder, as a cosmological model builder, do I really think that these things are necessarily something that I have to be terribly worried about when I'm saying, well, I'm going to build an inflation model or a dark energy model or something like that? And I would say that my argument is probably not. That these are formally useful, but they don't seem to, well, or they certainly seem to be in a lot of tension with what we see in the data in the real world. And perhaps a better example of this than, maybe inflation didn't happen, you can get out of it that way. But there's also the question of dark energy. And here, for example, is a characteristic, a bound on the equation of state of dark energy. And this is just data, right? How close are we to de Sitter space in dark energy? And you have some wiggle room there, but basically what the data favor is something that's very, very close to a de Sitter-like solution, which would be completely in tension with the de Sitter-Swampland conjecture. So in order to make this kind of picture of dark energy consistent with these swampland conjectures, you now have to say, okay, now the dark energy is dynamical, which makes the coincidence problem that much worse, because not only do you have to explain why the dark energy density is what it is, but you have to explain why we happen to be living at that point where it's just like, it's that very brief time when it's even dynamically relevant, because at late times this has to decay in order for the de Sitter-Swampland conjecture to be observed. So if we're building models of the actual universe, if we're really trying to talk about the real world, do we have to care about this? I would argue probably not. I mean, if the universe looks like it's de Sitter, and in the early universe, for example, in inflation, or even worse, dark energy today, if we appear to be living in an approximately de Sitter solution, and string theory doesn't support de Sitter solutions, you have two choices. Either you argue that the data are telling us something that isn't true, or that our conclusions that we gain from the data are wrong, or maybe that it's just string theory happens to be the wrong theory to describe that. And what these conjectures are really telling you is that you need to come up with some sort of other UV completion, some other way to understand the quantum gravitational limit in order to explain the world we happen to live in. So with that, I will end, and I think I'm actually reasonably close to being on time, so I'm sorry we got started late, and I'd be happy to take questions.
Great, thank you very much, Will. We're not going to applaud on these, but just imagine everybody applauding for the moment. If anybody has a if anybody has a question, can you raise your hand? Okay, Cliff, can you ask your question?
Hi, it's actually more of a comment than a question, but it's just that I was with you to the last slide here because you were making a distinction, a fair distinction between these conjectures and string theory predictions. And I accept your argument that the conjectures are in bad shape phenomenologically, but that's not to say that the string theory inflationary models are in bad shape, right? It's in your plot.
Fair enough. I mean, although this is something that kind of confuses me actually about the way the sort of the debate over this stuff has gone, is that it's really easy to write down string theory models that violate these, that appear to violate these conjectures in one way or another. And I think this DBI inflation is a really nice example of that, where you can, I mean, these are string-based models, and they immediately run into strong tension with both de Sitter and transplanking censorship. So I leave it to guys like you to explain to me how one is supposed to reconcile those two things. Yeah, I mean, do you have anything to say about it?
Well, I do, but it's not very deep. It's just that the conjectures are wrong. Or actually, a better way to say it is that there's a whole suite of conjectures, as you said, and there's a complementarity process whereby the conjectures that are most likely to be true, like the one that you started off with about the weak gravity conjecture, are not very informative at low energies, because you can always fix them close to the Planck scale, and the ones that are very strong and make very important and constraining statements at low energies are almost certainly wrong. And so it's hard to see if there's useful guidelines there.
Yeah, do they let you go to California anymore? Like
Well, no, as it happens, not.
Okay, we have another question from Gazelle.
Guess just one comment. Has there been any response from them regarding the inflation? Because I vaguely remember they said they're at conflict with, with dark energy, and they favor quintessence, but somehow inflationary models are not relevant. Is that something to do with high energy, low energy again?
At least as I understand the viewpoint here, I mean, this is asking me to put words in other people's mouths, but at least as I understand the way this is being viewed, is that this is considered to be like really strong evidence for ekpyrotic scenarios or something like that. I mean, the idea here is that inflation just isn't a self-consistent theory, and that you need to move toward collapsing universes and stuff like that. I have a lot of problems with that point of view, as you might imagine. But I think that's the argument being made, at least as I understand it.
Okay, and then on another question regarding this, I hadn't noticed the fact, regardless of the Swampland, the convex versus concave potentials, which you're saying now we are, I guess, favoring the concave models more than convex. And so, I mean, old days, these problems often have fine-tuning problem with initial condition. That's why chaotic models were more popular, because you have a, yes, is that an issue here, or have you checked?
Yeah, I mean, absolutely. I have, and in fact, there's more issues than that. I have a whole bunch of, I could go and talk for another half an hour about what this means in terms of for these models. In particular, you also end up having the danger that you recover. Let me just like sort of, basically bottom line here is that in these hilltop type models, what you find is that your condition for avoiding internal inflation, is that eta has to be bigger than about a square root of 3 or so. So you have to have a really, really large second derivative of the potential. Otherwise, you inevitably end up in a state of eternal inflation. And in particular, this doesn't really, the refined swampland conjecture gets you back into a situation where you have to worry about having, for example, eternal solutions again. And one of the big hopes was that these swampland conjectures would rule out crazy things like eternal inflation. And it turns out that if you fix them up well enough that they admit stuff like the Higgs boson, you get eternal inflation back no matter what. This is a rough estimate, and there's some papers that have been written since that are talking about more of the details of it, suggesting that maybe you still can barely, marginally rule out eternal inflation, but it becomes an issue again. So all this stuff with these concave potentials, you end up with fine-tuning problems, you end up having to worry about internal inflation, and all of those things just come all the way back as soon as you admit them as phenomenologically viable theories. Does that answer your question?
Yeah, thank you.
Okay, thank you. There are no other questions. Let me thank you very much, Will, for doing this.
Thank you. I'm sorry for the glitches at the start, but I'm glad it ended up working out okay.
No, it worked out very well. So everybody should unmute, and we should actually applaud Will, and then we'll meet again next week. Okay, thanks.
Thanks, guys.
Thanks, Will.
Thanks, you.
Okay, bye everyone.
Y'all have a great day.
We can consider this as a hint. So they have hints on the schematic, for example, for